Okay, so last lecture we solved the idealized waveguide, and we just used this method of transforms to solve the wave equation. Very simple, of course, mathematically a little bit, maybe a bit out of your comfort zone, maybe not. But essentially the technique is the important part because it always works to some extent. And so to talk more about that, to go further down that bold claim, we're going to look at the next most complex waveguide. So, our idealized waveguide, we had basically algebraically beautiful boundary conditions of a pressure release boundary at the surface, pressure release boundary at the bottom. Very unrealistic because, of course, the bottom is not pressure release. So what does our waveguide look like when we amp up the realism? Okay, so we have some waveguide, capital H deep, and we're going to have some density and some sound speed in the water part, right? Very well known. And of course, I should say that this is homogeneous, right? So there's no mixed layer, there's no oceanographic features here. This is just a iso velocity, iso sound speed water column. Now, instead of making the bottom pressure release, we're going to say, well, let's also just put some density down there, rho 2, C2, and we'll put some attenuation as well, because the attenuation we know is very low in the water column, but in sediments and in rock we know there's lots of attenuation. Okay, so what does this look like? How do we attack this type of problem? Well, we sort of have three regions. We have this region up here, which we don't worry about because we know the pressure is going to zero. We don't care about the sound field in the air. We did that in assignment 2. Okay, we have region, so we're going to call this region 1 and this region 2. Okay, we have water, we have some bottom type, and we're going to say both of these are fluids. So we're already making some pretty bold approximations in the sense that we know that the bottom is not a fluid, it's solid, so it can support shear waves, but we're going to say we're just worried about compressional waves. We just care about sound here. Okay, so what do? Well, we had a pretty simple formula before. We said write the wave equation, solve the wave equation. That's all you need to do. We're just going to keep doing that. So we're going to write the wave equation in region 1, okay? And I'm going to use phi for the pressure field. And I'm just going to say we're going to be in 2 dimensions. 2 dimensions in Cartesian coordinate system, okay? So we have our d by dx squared, d by dz squared. We're not going to worry about y, which would be out of the iPad and into the iPad, or your screen, I guess. Then we're going to have our 1 over c squared and our time derivative. Okay? And we're putting our source in this waveguide. Okay? We're going to put our source at a depth of z prime, and we'll say it's at the origin as well. Okay? So this is going to be x equals 0. And, okay, fair enough. How do we do that? We're going to say it's an impulsive source, so we give it some source strength q, and then we just use the delta function to position it in time and space. Okay? So now we need to solve that. Do we have enough information to solve this? Well, not really, right? So what are our boundary conditions? We have the one boundary condition at z equals 0, but what are our boundary conditions at z equals h? Well, we talked about this a while ago, right? First of all, we need, capital H, continuous pressure, right? Okay. Continuous pressure, and we need continuous particle velocity. Of course, we talked about why that was. We wanted to avoid ripping apart space, right? So we need finite forces over infinitesimal distances. So how do we write that? We'll say so phi is our velocity potential. Okay, so now we have some boundary conditions at the bottom here, And if we want to use those boundary conditions, we also need to know what phi 2 is. So we need to write the wave equation in region 2. So what does that look like? Well, oops, I just noticed I put a little 1 up there. Okay. Looks pretty much the same. Looks exactly the same. It's the same physics, right? So the equation is going to be the same. The only difference is, what's our source? We have no source in the bottom, so big 0 there, okay? And this is going to be for z greater than h, okay? So now all we need to do is exactly what we did last lecture, okay? We need to solve these equations. How do we solve these equations? Well, we're going to transform from t to omega. We're going to transform from x, and I'm going to use p as a transform variable, right? And then we're going to deal with z. Just like before, in the idealized waveguide, we had to come up with a transform to deal with z. So we're going to come up with another transform that's going to look very similar to deal with z. So all of this, right, is going to turn our partial differential equation into algebraic. Oops. And actually, this is our partial differential equations into algebraic equations. So then we're going to have a series of equations. We're going to solve those. Solve. Then inverse transform. Oops, oh my God. Okay, so that's the recipe. Seems pretty straightforward. So let's just, let's do it. Oh, by the way, I should say, look at this nice picture here. This is a picture of Pekeris himself. And we're not following his solution exactly. I think this is a little bit easier solution. And in fact, I should say he solved it in terms of Z and R, so in an axially symmetric waveguide. As you saw from the idealized waveguide, right, we wound up with that that Hankel transform gave us the Hankel function, for the range term. We're gonna just ignore that because we know that in the asymptotic limit we get this exponential decay. So that it's we get the cylindrical decay or the exponential decay depending on the conditions. We're gonna follow that same argument, but just not worry about having to work in the cylindrical coordinate system. Okay. Bit vague, but I think it'll become clear as we go along. Okay, so we transform. Use our Fourier transform, take us from time to frequency, and that's going to give us good old Helmholtz equation. So we Fourier transform from time to frequency, get the Helmholtz equation, and then we're going to use the same transform on x to get us from x to p, the transform variable. And that's going to give us this equation in region 1. And, I'm going to skip some of these details, but of course, feel free to convince yourself that I haven't made a mistake. And I'm going to say eta 1. So there's your doubly transformed field. The delta functions do their job. And let's define what eta 1 is. Eta 1 is just to make my life a little bit easier, on my left hand here. I'm just condensing some of the wave numbers into one variable. And in region 2, in the sediment, we're going to have the same thing, but slightly different. Right? Now we're going to have eta 2. We have phi omega p, which is the doubly transformed field on the right-hand side. We have a big, nice, easy 0. Okay. And of course, in both of these cases, you know, kj is equal to omega over cj because there's two different sound speeds in the two different layers. And we want some attenuation, right? We said we had some attenuation in the second region. So in 2, attenuation can be included in C. And I think this is going to make sense here. Basically, we say, you know, C2 is equal to C naught plus I alpha. And that makes K2 equal to omega over C naught plus I alpha. Why is that useful? Well, let's just go off a little aside here. If K is complex and you have an e to the I k r, right? Now all of a sudden you're going to have an e to the I k real part r e to the minus k imaginary r. And so this is going to give you an exponential decay. In other words, it's going to do the job of attenuation, while this part is going to be your wave, right? So this is just a handy, this K2 equals omega over C naught plus I alpha is a very nice way to include attenuation without having to, you know, add an extra complication. Okay, so let's solve. We wrote down our equations, now we need to start solving them. So let's solve 2. And what are we going to solve 2 with? Well, let's go back because there's one boundary condition we didn't talk about here, right? What happens to waves going this way? Radiation condition. So we actually have surface, we have 2 at the interface, and 1 at infinity depth, okay? So let's apply that radiation condition right away. So solve 2 with radiation condition. Okay? So phi 2 omega p is equal to phi 2 omega p at h e to the minus I eta to z minus h. Okay? This is for z greater than h. I think that's pretty easy to see from the equation. Boom, right? So we want to put some limitations here on eta, because eta, of course, can be complex, right? Let's write that here. Can be complex. Because now we have e to the I eta, and eta can have a real and imaginary part. So we're kind of following the same logic as this little argument here. We want eta, the imaginary part, to decrease the signal as it propagates, right? We want it, otherwise it would be artificially be unphysical, right? So if this exponential had a positive part that went as z, and that would mean the signal would be amplified as it propagated, just wouldn't be physical, right? So what do we need to, how can we enforce that? Well, we can just actually put a requirement on eta. So we require, actually let me say, put it this way, the imaginary component of eta 2 to be less than 0, okay? So we have this nice little solution for phi in region 2. Let's work on region 1 now. And as I was saying earlier, to solve in region 1, we need another transform. We're going to go z to q, okay? So our transform variable is going to be q. And in this case, we're going to use a finite Fourier transform. This time not a finite sine Fourier transform, but the whole thing. And the definition is going to be that the transform field be integrated from 0 to h. So it looks very familiar, except we're using the full complex exponential instead of just a sign. And the inverse then will be given by 1 over 2 pi from infinity, or negative infinity to infinity, the transform field, transform field, transform function, and dq. Okay? And of course, what are our reasons for choosing this, and all the details of that you can get into. But the nice thing here, without going into too much detail, the nice thing here is that let's call this something. Let's call this f tilde of d squared by dz squared of phi 1 is going to be, oops, something's wrong here, okay, minus q squared transformed field phi 1q, okay? Save that for, you're relaxing maybe after going to the beach or something. You can convince yourself that that's true. Okay, so we apply that transform, and then we solve the equation. So, I'm apply transform to equation in 1, then rearrange. Okay, I'm doing 2 steps in 1 here. So we have our triply transformed field, phi 1 omega pq is equal to minus q. And what happens to our source term, okay? Well, we end up with minus iq z prime. We have to evaluate the field at h because of our integral, right? QH. And then we have to evaluate it at the surface as well. Okay, so we have some, I've actually used the prime notation here. Right, just to condense things. So this has applied all of our boundary conditions, and this whole thing, well, okay, I'm just going to erase that. This whole thing, when we simplified, right, we're going to have this over the wave number, or over the combination of wave numbers. We're going to have eta 1 squared minus q squared, okay? So let's see, q prime, phi prime is equal to d phi dz, okay? So now all we need to do, and I think I need some brackets here, don't I? So, okay, skipped a bunch of steps there, but I think you're going to trust me. Now all we need to do is inverse transform. And, that is a pretty big job. So I'm going to say with help. And again, books, tables, Wolfram Alpha, those are all your friends. And we need to exploit all of these boundary conditions that we have to deal with now. We need to recompute these oops, shoot. One omega p. We have to recompute these in the transformed variables that we want, okay? So these are all determined by original boundary conditions. Okay? So what do we end up with at the end of the day? So again, we're going to skip some of the detail just to make this not take forever. So if we transform over P and over Q, and we just end up back to our solution of the Helmholtz equation, we're going to have Q over 2 pi, and I'm going to call this F1, which is a function of eta 1, eta 2, e to the I px dp. And this is going to be for z in between 0 and h. So that's in the water column. And our equation 2, similarly, same order of transforms. We're going to be stuck on the same transform, expressed as an integral e to the I px dp, and this is for z. Less than, z greater than h. So so this is in 1, or water, and in 2, sand. Okay, or the bottom. So obviously there's a bit of finagling there, but really it's just some calculus, some algebra. F1 is this function here. Oh, I should also say, before I get into that, B12 is a ratio of densities. F1 is this function here, and you can really just see that this like complicated function really comes from just evaluating the boundary conditions and solving two equations simultaneously, essentially. It's really actually not that ugly. It's just some sines and cosines that one has to be relatively careful about keeping track of. But it's really not that bad of a problem. And it follows very closely what we've done in the previous lecture in total completion, total detail with the idealized waveguide. So, if you're feeling a little overwhelmed, don't be overwhelmed. This is just algebra at this point, really. And here, I'm going to say, I have to use this little symbol here, z less than or z greater than, right? You can see in the first term I have z less than. Z less than is lesser of z prime. So it's just a condensed way of expressing whether you're above the source or below the source, because that changes algebraically what this f function looks like. And in the bottom, we have slightly simpler sine eta 1 z prime e to the minus I eta 2 z minus h, and it's all over the same denominator. Eta 1 cos eta 1 h plus I, the ratio of densities, eta 2 sine eta 1 h. Okay, so pretty monstrous thing, but it's actually the important part is really, really simple. Okay, and this is totally the same as the Pekeris, the original solution. So similar / I'm going to just say identical, because I can, to Pekeris solution. except range transform is Fourier instead of Hankel. And so you can imagine what that might look like. Instead of having some exponentials, you're going to have some Hankel functions that are going to asymptote to exponentials. Okay. So how do we evaluate? Now this is, let's get out our highlighter here, because now we're talking about this equation and this equation. We need to solve these integrals, right? And the question is, how do we evaluate these integrals? Well, might be more or less obvious to some of you, but it's all about the limits here. We're talking about integrals along the real axis from negative infinity to infinity. So it's just screaming out. It's screaming out for Cauchy's theorem. So let's just remark a few things here. Both F1 and F2 have poles in the denominator. Well, okay, poles are zeros in the denominator. Have poles, which is to say they have zeros in the denominator, so the function goes to infinity at these different parts on the complex plane. And if that's not enough for you to think, oh my God, we need to use the theorem of residues, Cauchy's theorem, then I don't know what is. Now, no problem. We're going to get into just what that is on this next page. Okay, so the denominator is equal to eta 1 cos eta 1 h plus I b1 2, the density ratio, sine eta 1 h. And you might be thinking, okay, what poles and what are we talking about here? Eta, right, is a function of p. P is what we're integrating over, right? Here's the complex plane where we have real p in this direction, imaginary p in this direction, and we're trying to integrate from negative infinity to infinity. So we're actually trying to just integrate along this line. And the idea is that if we choose just, half of this plane, we can compute where all these poles, or in other words, zeros of D, are. And then use the theorem of residues. Okay, so what's the theorem of residues? Okay, bit of a side. Bit of a side here. So the idea is that actually what you do is you do a contour integration. Okay, so you have this piece, which is the, so this first piece here, and then you have this second piece, right? And if you think about this integral, there's going to be one of the first piece is going to be just that, and then the second piece is going to be actually, oops, thought I changed colors. Second piece is going to be a little bit more complicated because it's along some contour C, right? And you can just say, okay, that's going to be the whole thing, and our goal here, or what happens is essentially this part goes to 0. And so then you have the theorem, the residues here are just equal to the original integral that you're trying to solve. Okay, that's the very hand-wavy roadmap of what we're trying to do here. Okay, so in general, then we can just say here quickly, and this is like I said, might be a review for some of you, might be a little opportunity. Pause the video, go do some Googling. The definition of the residue. So the residue of f at z naught is a limit as z goes to z naught of z minus z naught f z. Okay, here, confusingly here, sorry, I should say in complex plane z equals a plus ib. We're not talking about, this is just general here, we're not talking about depth, just in case you're wondering. So if f of z has a pole of order k at z equals z naught. So for a higher order, so residue of f at z naught equals 1 over k. For a higher order pole, definition is slightly more involved. dk by dzk okay. K is a whole number. Okay, so that's a little aside here. Just a little roadmap, what we're trying to do. The original thing, right, is to solve this integral from negative infinity to infinity. So we break up this contour, and we use this Cauchy's theorem to say that, well, the answer to that integral, right, that's the thing we're trying to find, is just this sum of the residues. The residues are defined by these two definitions, and so all we really need to do is figure out where these poles are, right? So we need to find out, this is the important part here. Where are these poles? And then we can evaluate all this and actually evaluate the sum of our integral, right? So the next step is find the poles. And we have this equation D. We just need to figure out, okay, well, when does that equation go to 0? So the roots, okay, roots of D, find them. Just in case, need a little entertainment. Okay, so D equals 0. We just can solve that equation very, very quickly. We have the tan of eta 1 h equals I eta 1 over the density ratio eta 2. Okay? So we can write the whole thing in terms of eta 1. We get tan eta 1 h equals minus eta 1 over the density ratio, and now we're going to have, whoops, k1 squared minus k2 squared minus eta 1 squared, right? And now let's simplify this a little bit. So we're using some relationships between the wave numbers here that we, same way we exploited last time, right? Eta 1h is going to equal m pi, right? Because we know that we're going to have, when we take the inverse tan, that we can have, repeated solutions here. So this equation is looking a little bit transcendental. Okay. Where m is equal to 1, 2, dot, 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 m. Okay. So that kind of makes sense because, we know that we're going to have an infinite number of modes, just like we had with the idealized waveguide. So this is kind of encouraging in that sense. So m is our mode number. Okay. And the modes are the residues, right? Of our two equations that had d as the denominator. They're the residues evaluated at the poles. Evaluated poles. We're in the p plane, so I'm going to call those poles PM, okay? And, PM come from equation 3, right? So this is equally deserving, this equation here, because really this is telling you so much about the system. It's telling you about where those poles are, and that's just telling you the answer to the integral. And so in the same way where we sort of made our answer discrete, right, this discrete summation, with the idealized waveguide by using the finite sine Fourier transform, now we're also coming on that same discrete formulation here, but it's coming out of the theorem residues, okay? M is finite. Because we required the imaginary part to be less than 0, right? So that's very important. If we hadn't put that requirement in, or if we had, say, if we'd chosen, for instance, let's, let me go to a new page here. So if we hadn't put that requirement in, we'd obviously just have this unphysical answer where waves could increase. Amplitude of waves could increase as they propagate away. But what about if there's no attenuation? In the bottom. So if there's no attenuation in the bottom, then eta 1 looks like this. This would always be real, right? And so all of our poles, PM, would lie on a real axis. Oops. And they would be between minus K1 and minus K2. Okay, just an interesting side note. But at this point, so what do we do at this point? We have this this transcendental equation. We want to solve this. So solve So we can obviously just do it numerically. And that would be find PM and M. But of course, let's see what insight we can get using analytical approach. And what's the best thing we can do? Simplify the equation by, let's do a Taylor expansion. Let's approximate the equation a little bit. Linearize it. So if we do this route, we can write eta 1 h is approximately equal to m pi, and then simply eta 1 h over b 1 2 k1 sine alpha c. And recall, alpha c is the critical angle. It's just the cosine, inverse cosine of the ratio of the wave numbers, right? So we did that when we looked at reflection from the bottom. And this is the critical grazing angle. Okay, and this is when K1 is nearly real. In other words, the attenuation of the water column is very, very small, which is true. So in that case, eta 1, eta 1 m now, right? So we're saying that we have a bunch of these solutions for eta 1, which are countable, I guess, indexed by m. It's going to be m over pi h 1 plus b12 k1 h sine alpha c. And we actually have a name for this approximate h now. So since we've changed the answer a little bit, we've changed some of these parameters. This is known as the effective depth. And I'm going to call it little he. Okay? Now equally, eta 2m is equal to ik1, or approximately equal to ik1 sine alpha c 1 minus m squared pi squared, right? K squared he squared sine squared alpha c, right? Comes out of our relationship. And we can actually write a solution for PM, right? So these are all in terms of the effective depth. So what does this effective depth actually mean, right? Well, let's just do a sketch again. Here's our waveguide. And I'm going to draw poorly. I'm going to use this here. Look. This is going to be our effective depth. Okay. So here's the depth of the true depth. Here's the effective depth. And let's just take a step back and think, okay, we know that the solution's modes. We have this theorem of residues that allows us to sum over a bunch of modes. We know they're somewhere in the complex plane. We have to do all this work to actually figure out where they are. But let's think intuitively what the answer looks like. Well, we know in the real world solution that this is going to be exponentially decaying somehow, right? And then we're going to have the mode's going to have to be continuous across here, and then we're going to have this has to go to 0 here. We're going to have some combination of things that oscillate and things that decay. Okay, right? Fair enough. I know it's a bit hand wavy, but it makes sense, right? With the idealized waveguide, we just had things that oscillate between two pressure release boundaries. So the idea with effective depth here is that basically we're saying, well, this is a depth at which P equals 0, essentially. And since we really care about what the solution looks like in the water column, well, why don't we just say, if we have this kind of P equals 0 effective depth to first order, now this is, pretty badly drawn here, but we can say, well, we have this approximate solution. and actually does a really good job of describing the mode shapes in the water column, and a bad job in the sediment, but we're interested in the water column. So it does this really good job of describing the mode shapes in the water column without having to go through too much difficulty in calculating the mode shapes using our transforms method, right? So all we really have to do is calculate the effective depth and then compute mode shapes. Oops. From the ideal waveguide solution, which we know are just signs. So by compute, I mean very, very straightforward. So this effective depth really controls the trapped mode shapes. Of course, it's an approximate solution, but pretty powerful approximate solution. So let's just do a quick recap and then see where we're at. So we essentially we took our two layers. We wrote the wave equation each layer. We transformed 3 times to get 2 algebraic equations. We solved the algebraic equations, and then when we were transforming back, we basically decided that the theorem of residues was the only way or the best way to solve that final inverse, right? And then so when we came across the theorem of residues, we said, okay, we have to find the poles, and then the solution to the integral will be a sum of the residues over all those poles. So we had that sort of same idea of summing over mode shapes. And then we'd use this effective depth approximation to figure out, well, how's a faster way we can calculate those mode shapes as well as those pole locations, okay? That's what we've done so far. So let's figure out, let's talk about one of the other assumptions, or sort of, yeah. Let's talk about branch points. Let's talk about branch points. So one of our steps here was calculate residues at the poles, PM, to approximate the solution. And so the question is, why approximate? We forgot about branch points. And I'm pretty sure Pekeris forgot about branch points too, so we shouldn't be too worried about it. And basically the idea is we have eta 2, right? Our definition of eta 2 was k2 squared minus p squared. K2 is equal to omega over C2 plus I alpha, right? We had written some sort of omega over C naught plus I alpha, whatever. And we restricted the imaginary part of eta 2 to be less than 0. So alpha is less than 0. So we can write eta 2 as omega over C2 squared minus p squared plus I alpha. Okay? So we have branch points. At P equals plus or minus K2. Since this really is a complex number, and essentially the idea that if we think about this as a polar, in polar terms, we can go around 2 pi and have the same number essentially a whole bunch of times, okay? Multi-valued, function multi-valued, okay? So, whoops, man, I really need to get better at drawing straight lines here. So here's a complex plane in P. So a negative K2. The idea was that we were going to integrate along the real axis. They were going to integrate around the contour, and that was going to be all that we needed to do, right? So the idea was that we would express this integral, and I'll call this C. We would break down the integral in terms of these two paths, but of course, because of this branch point, we need to actually do a little cut here. And go around it, okay? So what does that look like in the end? Well, so recall our solution from equation little 1, right? So we had 2 pi I. Now we're talking about the sum over the residues of our big function f, evaluated at the PMs or the eta m's as that, propagates up, times, so I'm running out of room here, e to the I PMX, right? That was going to be all of our solution, but now we also have to include the branch cut for completeness. dp, right? So that is, let's call this something. Let's call this EJP after the people that named it, but I don't know the names off the top of my head. Okay, sorry about that. And of course, similarly for phi 2 omega, so the solution that we had was not looking so bad. It was this 2 pi I times the sum of the residues. So the etas evaluated at the poles, e to the I PMX, and then plus this EJP cut, F2, oops, eta 1, eta 2, e to the I PX dp. Okay. So how do we evaluate the integral along that path that we haven't even fully defined? It's a bit annoying, okay? So we need to investigate this a little bit more closely. Whoops. To evaluate along the EJP cut. First of all, let's recall that eta 2 must be negative, right? And that's everywhere. Must be negative everywhere. And you can choose it to be real. On the cut. With phase. I mean, we can choose the cut to be any path we want, right? Phase negative pi or 0, respectively. Okay, so we're just defining what the actual cut looks like. And so that causes the integral to look like, q over 2 pi with the cut that we've defined, f1 eta 1 eta 2, and then we're going to have we have the e to the I px dp. So what does this actually look like now? Well, it's just going to be from minus infinity to infinity of eta 2 over square root k2 squared minus eta 2 squared f1 eta 1 eta 2 e to the minus I square root of k2 squared minus eta 2 squared d eta 2. Oops. So what does this EJP cut represent? Well, it represents the continuous field. Physically, what does this represent? The continuous field and the head wave, which is the wave that propagates along the interface at the critical angle. And what is this continuous field? More, what does this continuous field actually represent, or what is it? How do you summarize it? What makes up of it? It's the steep energy. Okay, so basically energy that's propagating directly into the bottom. This is steep energy that penetrates bottom. And in deep channels, this can be the direct and surface arrival. And of course the head wave, the head wave we sort of discussed earlier, but it's this wave that propagates at the when you have the critical angle, critical grazing angle. Head wave propagates along and parallel to interface. And has this evanescent component, of course. So all of this to say that, we have essentially, there's physical meaning to each part of our solution. And so just like, with in the ideal waveguide where we talked about the different modes having different angles of propagation, we can also break down our Pekeris solution where we have these, we have this modal components, and that's going to be represented by the residues. And then we're going to have this head wave component, and then we're going to just have, near the source, energy propagating right into the bottom, energy that propagates along the interface. This is the EJP, right? And the direct path, and sometimes the surface arrive path if the bottom's far enough away. Right, so we can actually algebraically isolate each part of the field, and you could plot, say, just the head wave by evaluating just the EJP and setting the rest of it to 0. So okay, that's it for the Pekeris waveguide. We've solved the whole thing in an hour. That's quite a formidable task. So thanks for sticking with me.